Welcome to my classroom. In this fuel cells and batteries course, we have been discussing about high temperature fuel cells. In the previous lecture, we have discussed about molten carbonate fuel cells, where we have seen the principles of molten carbonate fuel cells, various electrodes that are being used for molten carbonate fuel cells, and different electrolyte materials that are being used for molten carbonate fuel cells. And we have seen that the average temperature of molten carbonate fuel cells is around 650 degrees Celsius. They are used in the range of 500 to 700 degrees Celsius, right? Now we are going to discuss about one of the interesting and very high temperature applications of fuel cells, where we are going to make use of ceramic membranes as the electrolyte material for this type of fuel cells. So where you can operate your fuel cells around the temperature even 800 to 1000 degrees Celsius. So such materials have been developed for electrolyte, cathode and anode materials. So we are having one of the finest fuel cells, which is having most efficient output we get with respect to electrical efficiency, as well as if we are utilizing the heat to make steam production. So in that case, we are going to have around 80% of efficiency with this type of fuel cell, which is solid oxide fuel cells. Okay, it is one of the most effective devices which have been invented so far. Here, unlike other other means of converting electrical energy from fuel, here the chemical energy is directly converted into electrical energy. That is the advantage of our fuel cell. So in this type of high temperature solid oxide fuel cells, where we are going to have electrodes and electrolytes which are made up of ceramic materials, so that we can have a very high operating temperature around 800 to 1000 degrees Celsius. So we don't need any precious metal catalyst, because that reaction operating temperature is very high. Okay, so maximum we'll be using some porous nickel as the material here. Okay, and this biggest advantage of using such solid oxide fuel cells is this is having some advantage over the molten carbonate fuel cell. In molten carbonate fuel cell, we are using a liquid electrolyte. Here it is completely a porous solid electrolyte we are using. Okay, so the ceramic material, when it is when the ceramic is stabilized with some metal oxides, we get some very good electrolyte material which can be used at very high operating temperatures. Okay, so even for here, this anode, if you look at, we don't need any precious metal catalyst. So any porous nickel can be used as the anode material. Okay, so even ceramic material itself can be used as or metal oxides can be used as the cathode material here. Okay, so we are going to have a high temperature of 800 or 1000 degrees Celsius. So here what we can use is, we should choose a proper material which can, all three materials like anode, cathode and electrolyte should be having similar thermal expansion. That we should take care. Here another advantage with respect to using this type of solid oxide fuel cell is, so they very fast kinetics, you have a wide choice of fuels. So whatever fuels that can be used in molten carbonate fuel cells, we can use this one. So minor difference between that molten carbonate fuel cells and solid oxide fuel cells is, in the solid oxide fuel cells, we are having a solid electrolyte. That's why it is called solid oxide fuel cells. Okay, where it is molten carbonate, where it means that the electrolyte is in molten state or liquid state. Okay, so there are various companies which are interested in this type of solid oxide fuel cell, like Acumetrix, General Electric, Ion America, Rolls-Royce and Siemens Power Corporation. So these are some of the companies which are interested in this type of solid oxide fuel cells. So in this lecture, we are going to discuss about the principles of solid oxide fuel cells, the various materials that are used as anode, cathode and electrolyte. Even molten carbonate, what we have seen, perovskite based electrolytes, right? So here also perovskite based electrolytes can be used. And more importantly, we are going to discuss about different type of ceramic materials, which even it is actually a composite material. We are going to use several materials to make this type of electrolyte for this application for solid oxide fuel cells. Okay, so and this operation is very straightforward. The solid oxide, what we need is, we need an electrolyte which will selectively allow the oxygen ions to pass through the membrane. That's all. So if oxygen is there, oxygen comes, when oxygen plus electrons will combine to form oxygen ions, So once this oxygen ion passes through the electrolyte and reaches the anode side, hydrogen and these oxygen ions will combine to form water and electrons. So this electron will be flowing through the external circuit. So the generating electricity. We know that the electricity produced here is DC current. So we have to convert the AC current to use it for domestic applications. Okay. So, but one thing we should know is along with this electricity generation, we are having a lot of heat is being generated. Moreover, the operating temperature is very high. So proper heat utilization has to be done so that we get overall efficiency around 80% in the power plant, which comprises of the solid oxide fuel cell. If you consider only the fuel cell, we are going to have at least maximum of 60% efficiency, electrical efficiency in this type of fuel cells. Okay. In this lecture, we will discuss about what we have discussed in previous lecture, that molten carbonate fuel cell advantages, disadvantages, and animation video of how this mechanism that is taking place in a molten carbonate fuel cell. And we'll look into some of the recent advanced materials which are being researched for application in molten carbonate fuel cells. Then we will look into the principles of solid oxide fuel cells and the various components that are present in the fuel cells. We'll look and discuss the advantages and challenges associated with it, and what are the reaction mechanism or various possible rate determining steps that can take place in solid oxide fuel cells. And we will see different design strategies, including whether we are going to have external steam reforming or internal steam reforming, or in absence of steam reforming. So that kind of topics we will discuss initially, and if time permits we will continue. Otherwise we will discuss about each desired characteristics of different components of solid oxide fuel cells like anode, cathode, electrolyte, interconnectors, and sealants. Okay, and we will discuss about the research status of materials of solid oxide fuel cells, and we will look into what is an interconnector, what are the desired characteristics of interconnector, and all these materials. So all this second of topic will be discussed in the next lecture. Okay. In the previous lecture, we have been discussing about molten carbonate fuel cells, right? We have seen that there are significant advantages in molten carbonate fuel cells have been done in the recent months, and there is a need to reduce the NIO dissolution, which is exacerbated if the molten carbonate fuel cell is operated at very high pressures, elevated pressures. Okay. So while other metallic and ceramic oxides are available, which do not dissolve in this electrolyte, like lithium cobalt oxide, which is also called as lithium cobaltate or lithium cobaltite, LiCOO2, most have an inferior electronic or ionic conductivity. So NIO therefore continues to be the basic cathode material of choice, and the various NIO composite materials have been reported in the past 18 months, which have been summarized in this table. So this is the latest research review R&D work that is being carried out in the past 18 months or 12 months associated with this particular electrode material for molten carbonate fuel cells. Okay, so here are the composite material which are made with this NiO, nickel oxide. So you have different methods have been followed, and what is their solubility, what is the comments have been given in this table. Please refer to this table for what is the status of different composition materials made with nickel oxide as the base. Okay, and because these composites have been made to reduce the nickel oxide dissolutions. Okay, because we want to operate at elevated pressure. So there is a problem of dissociation of that metal. Okay, so this is a typical representation of this molten carbonate fuel cell, which I wanted to show you in the previous lecture, but due to time constraint, I'm showing it here. So how it works, this is an animation which explains you what is the function of a molten carbonate fuel cell. So in a molten carbonate fuel cell, we have this CO2 and hydrogen is entering this side, and you have the right hand side, you have oxygen. So this is the reaction that is taking place. You have CO2 and water being the product that is being formed in this side. And on the other side also, you have carbonate ions are formed, and which reaches to the left hand side, where it combines with hydrogen to form CO2 as a product, and this electron flow through the external circuit. Okay, so that is a typical animation which explains you how the electrical current is produced. We know that it is a DC current which is being produced. Okay, so from the right hand side, what is happening? So we have oxygen and CO2 entering in this side. Okay. And see, carbonate ions are formed at this side, and that carbonate ions pass from the cathode side to anode side, and it reacts with the hydrogen to form electrons, which passes through the external circuit and forms water and CO2 as a product. With respect to circular economy base, from bio waste also you make use of molten carbonate fuel cells to produce energy. One such paper has been reported in 2018. You can go through it if you are interested. Okay, so coming to this today's lecture, we are going to discuss about these high temperature fuel cells, solid oxide fuel cells, which generally operate at around 700 to 1000 degrees Celsius. Here the advantage is, as I told you earlier also, we are going to replace the molten liquid phase electrolyte with some solid electrolyte, which makes it feasible to operate at different conditions, and the design simplicity is there. Okay, so there are cost reduction is there. Okay, and remember the thickness of this type of fuel cells is even like a wafer biscuit, no? So that much thin it is. You can see it is like 5 cells, which is of a length only 1.5 mm. So that is the way fuel cells. You can see with this comparison with the scale. You can see that with it's a 30 centimeter scale, you can see different size of this type of fuel cells. Okay, so that way this kind of fuel cell, which has a very thin things are there. You can see 5 fuel cells. One fuel cell stack with 5 fuel cells is a length only 1.5 mm. So that way it is very thin, similar to your. We are going to discuss about the principal history and R&D status of the solid oxide fuel cells. So the quest for better energy efficiency is intensifying in 2016 onwards, because the year in which the Paris Climate Conference happened, where there was agreement even in molten carbonate fuel cell. I told you about cement industry. 73 plus nations have promised in that Paris Climate Conference agreement to reduce the carbon dioxide emissions to make it net zero towards 2050 or 2100 year, right? So developers are increasingly looking into this type of solid oxide fuel cells, which can help to reduce the carbon emissions associated with the electrical generation because of its high conversion efficiency and its suitability for distributed generation. Whereas the conventional power stations or transmission setups are limited to only a efficiency of 35%, whereas these solid oxide fuel cells can achieve up to 50 to 60, or even with combined cycle, we can achieve even 70 to 80% overall efficiency. Okay. And these solid oxide fuel cells have the added benefits of long-term stability, a high fuel flexibility, and a relatively low cost. The efficiency of these solid oxide fuel cells can be mostly attributed to their operating temperatures of 500 to 1000 degrees Celsius, which is significantly hotter than the conventional cells. So what does that mean? This high temperature fuel cell means that we don't need any costly catalyst, similar to molten carbonate fuel cells. So here also we don't need any expensive, precious metal catalyst like platinum. Okay. Instead, we can use some significantly cheaper materials. Even ceramic materials can be used. Maximum nickel can be used as the catalyst, right? So the high temperature also means that the reaction kinetics is going to be fast, and we are going to have high energy density also. But unfortunately, the energetic conditions that the high temperature fuel cell results can cause some technical challenges also. And this is particularly true with, there are different designs of solid oxide fuel cell, which we are going to discuss. So particularly with flat planar fuel cells, we have some technical challenges, which is overcome by making a spiral bound type of solid oxide fuel cells later on. Okay, so you know that to start with, we know that in comparison to thermal power plant, these fuel cells, we know in fuel cells there is no intermittent energy losses, because if it is a conventional thermal power plant, first the chemical energy is converted into thermal energy, then the thermal energy is used to run some mechanical part where it is converted to mechanical work. Then that mechanical work is converted to electrical energy. If you consider hydrothermal power plant, okay, so water first is converted to steam. Then steam is used to run the turbine. Then the turbine is generating the electricity, okay, connected to shaft and motor and that. But whereas in fuel cell, we directly convert the chemical energy into electrical energy, because during the reaction itself, the electron is released and passes through the external circuit, and we are having the thing, okay. And coming to this type of solid oxide fuel cells, making use of this type of solid oxide materials have been since so many decades, okay. In the history, traditionally the ceramic materials are used, right? So these traditional ceramics, they are mainly based on clay based, but high performance or advanced ceramics are being developed from a fair wider range of inorganic non-metal materials also. And these advanced ceramics have the properties of high strength, high hardness, high durability, and high toughness. And what is a ceramic? If by definition, it is an inorganic non-metallic solid which is made up of metal or non-metal compounds, which have been shaped and then hardened by heating to a high temperature and then cooling it. Okay. So in general, these ceramic materials are hard and they are used as a corrosion resistant, but they are also brittle. Okay. And these ceramic materials have three different ceramic materials are known. You know that it is earthenware material, which are earthen, which have been used for decades, centuries. Okay, because our old ancient people also made all this type of things, right? Earthenware, stoneware, porcelain. Even before chemical engineering coming into picture, all these type of ceramic materials have been made by the ancestors also. Okay. So they have the technology and they have, that how these things are made this time. Coming to this type of solid oxide fuel cell, we are going to make use of ceramic based membranes also. That is why I was showing you that one. Okay, so there are different type of materials which are involved in the research and to be used as anode in the solid oxide fuel cell, particularly for making, other than hydrogen, we want to make use of hydrocarbon as the fuel. Okay, so if you want to make use of hydrocarbon, that is hydrocarbon utilization purpose, we want to use some anode materials, or we want to use some electrolytes which can be used like that, right? So different anode materials are being used for solid oxide fuel cells. So ceramic materials and cermet. And for one, that is for ceramic materials, utilization of ceramic material is focused on finding a new fluoride based or perovskite based material to function as the catalyst, anode catalyst. Okay. And what is cermet? What is that name refers to? Cer and met. Combinedly, it is called as cermet, where ceramic and metal combination. Okay. It is a composite structure of a ceramic and a metal. And any case of any class of a heat resistant material which is made up of a ceramic and a sintered metal are called as cermet material. So we are having ceramic based anode materials and cermet based anode materials. Okay, so coming to the silicon carbide, regardless of ceramic membranes form and dimension, and it is made up of some inorganic materials such as silicon carbide, zirconia oxide, aluminium, or titanium. Okay, these are some of the basic inorganic materials. Okay, so from which we can make ceramic membranes. And if you consider the silicon carbide, why we have to go for the silicon carbide is, it is the second hardest material globally, only which is beaten by the diamond. Okay, so which is diamond, we know the hardness of the diamond, right? So this is the second material which is more harder except for the diamond. Okay, so diamond is more strong, harder than this. This is the second most hardest material which is known globally. Okay, so that way, by utilizing such a hard material, solid oxide material, which gives us a high quality and robust membrane with a long working lifespan. Okay, so if you are incorporating silicon carbide, which is a semiconductor which contains silicon and carbon, so the silicon carbide is linked to unique advantages such as providing some porous support structure which only filters water, which can permeate, while other impurities are getting rejected from this membrane. And besides that, the silicon carbide will provide us some high flux. Okay, mass transfer can be high. It will provide a very good chemical resistance under different pH condition ranging from 0 pH to acidic pH or neutral pH or up to alkaline pH, is to 14 also. And when you incorporate the silicon carbide material, we get some thermal resistance up to 800 degree Celsius. Okay. And there are new materials which are being even used as the anode material. So if you look at advanced ceramics, which are also called the new materials, so they are not generally clay based. Remember, okay, it's not that all the ceramics are clay based. Instead, we can make even ceramic, advanced ceramic material based on oxides or non-oxides or combinations of the two also. Okay, in general, these advanced ceramics, two oxides which are widely used are alumina and zirconia. Okay, so alumina means Al2O3 and zirconia ZrO3, O2. Okay, so these two are the widely used oxides. A combination of two oxides can make one advanced ceramic material. So even non-carbide, non-oxide materials are also used, such as carbides, borides, nitrides, and silicides. And for example, you can use boron carbide, which is B4C, silicon carbide, and molybdenum disilicate. Okay, MOSI2. And even in modern medicines and advanced ceramics are being used as a bioceramics, which plays an increasingly major role, because these bioceramics once made, no, such as alumina and zirconia, are hard, chemically inert material, so that can be polished to a high finish. So that way they are preferred to use as dental implants or even bone substitute in orthopedic operations such as hip and knee replacement. So we are in vivo, we are putting it inside the human body, such a type of advanced ceramic materials in place of metals. Okay. So that is the usage of these new materials. In this solid oxide fuel cell, here also we are going to make use of that. So that way we are going to have a typical solid oxide fuel cell which is similar to any other fuel cell. Here the electrolyte is different. So here electrolyte yttrium doped zirconium oxide is being used as the electrolyte, one of the example. So which will selectively allow the oxygen ions to pass from the right hand side to left hand side. So here you can use anode material, nickel oxide, yttrium stabilized zirconia, thermate can be used. Okay, so we can supply hydrogen from the left hand side in the anode side. Hydrogen and any hydrocarbon can be sent as a mixture also. So hydrogen will combine with this oxygen ion that is coming from right hand side to left hand side. So we have water being formed and the electrons formed. The electron formed will go through the external circuit, forming the EMF generation. And if you are sending, for example, any hydrocarbon, alkanes, CXH2X plus 2, then methane, if let us consider the simple case, methane goes with, again, reacts with these oxygen ions, an ion, to form water, CO2, and releases more electrons. So that way, if you are using hydrogen, you are going to have 2 electron production. If you supply a hydrocarbon, there will be 8 electron production there. Okay. So what is the role of the electrolyte here? It does not allow the reactants to pass through to the other side, and we are having it selectively only allows oxygen ions to pass through it. Okay. So what we are supplying in the cathode side, oxygen being supplied. So the reaction taking place is oxygen. Those electrons formed on the left hand side will go through external circuit and reach here. So you have oxygen reacting with electrons to form oxygen ions. Okay. And here there will be another material in the solid oxide fuel cell which is called as interconnector material. We'll discuss in detail about that later, but it is generally made up of magnesium, strontium, doped lanthanum, chromium. Okay. And the reaction taking place already I showed you here. So what is the reaction that are taking place if you are sending a combination of hydrogen and carbon monoxide? Then you will have hydrogen forming water and electron, and if carbon monoxide is there, that also consumed in this reaction at the anode side. So carbon monoxide and the oxygen anions will combine to form carbon dioxide and release electrons. And in the cathodic reaction, already as we seen, oxygen will react with the electron that is reaching to form oxygen ions. And the overall reaction, when we use hydrogen and carbon monoxide mixture as the reactant entering in the side, so we are going to have H2 plus CO plus O2 giving H2O plus CO2 with release of energy, heat also. Okay, so we know that the reactions are exothermic. That heat has to be utilized well. So that is the objective. And if you look at the membrane electrode assembly, that is membrane electrode assembly, we have discussed in detail in the PEM fuel cells. It is made up, it's a sandwich made up of electrolyte between anode material and the cathode material. It's a typical XRT diagram, a same image of a planar solid oxide fuel cell, where you have at the center electrolyte, which is yttrium stabilized zirconia electrolyte, which is around micro mm, 20 micro mm only. But actually, these are different. One layer will be very big, that is acting as the support. So based on that, we can say electrolyte supported solid oxide fuel cell or anode supported solid oxide fuel cell. When we say electrolyte supported solid oxide fuel cell, the electrolyte layer will be bigger one. So here you can see the thickness of anode, it is very big. So you can say that this is an anode support. Anode acts as a support of this fuel cell. So anode supported fuel cell, which is 1.5 mm thickness. This electrolyte thickness is 20 micrometers. And we have cathode material, which is 45 micrometers. Okay, so we are going to have a interlayer also, which is having 10 micrometers. Okay, so this is a typical ME assembly, which I wanted to show you. And what is happening here in this one, as I told you, you are having an anode layer, electrolyte, and cathode layer. So cathode, we are having, what is that? We are having a fuel entering in one side, that is hydrogen and carbon monoxide are entering. Let us say, in that case, hydrogen reacts with these oxygen ions. So actually, where we are getting these oxygen ions? Actually, this oxygen ion, oxygen is entering from the cathode side. So oxygen reacts with this electron that has reached from anode side to cathode side, and it will form oxygen ions. These oxygen ions will be selectively passing through this electrolyte, which is oxygen ion conducting electrolyte. Okay, so that reaching the cathode side. So we have oxygen ions here, and this fresh we are supplying hydrogen and carbon monoxide mixture. Okay, and this hydrogen reacts with oxygen ions to form water and release electrons. Carbon monoxide also reacts with oxygen ions to form carbon dioxide and releasing the electron. These electrons will be going from anode side to cathode side to external system setup, and that is where you are going having the electricity generation. Okay, EMF generation. And this is again the same with representing in different diagram phase. So oxygen is air is entering in the cathode side. So porous cathode, porous anode, and electrolyte. So the reaction taking place already we have seen. So these electrons are emitted from the anode side, and they pass through the external circuit and reaches the cathode side. Okay, and in the anode side, usually nickel supported on yttrium stabilized zirconia. What is happening here? Water and CO2 are the major product which are being produced when we are using hydrogen and carbon monoxide as the reactant, which reacts with the oxide ions. Okay, electricity is generated by the electrons ejected during this process. And what is the electrolyte doing? The role of electrolyte is it is allowing the oxide ions to pass from the air electrode to the fuel electrode. When you say air electrode, it is the cathode. When I say fuel electrode, it is the anode. This air electrode refers to where we are sending air, that is air electrode. Where we are sending fuel, that is fuel electrode. We know that we send air to the cathode side and we send fuel to the anode electrode. Okay, so that way we should know which electrode what we are sending and what is the reaction taking place. What this cathode is doing? This cathode receive from the air, it will take only oxygen, and oxygen will receive the electron which coming through the external circuit, which will form the oxygen ions. Okay, and most of these electrochemical reactions at a three-phase boundary, TPB we generally call it as, which are defined as the site where the ionic, electronic conductor and the gas phase are in contact. That is where the electrode, electrolyte and the gas phase are in contact. So the TPB characteristics have a very large influence on the electrochemical performance of the fuel cell. So we should know three type of possible rate determining steps are there. Okay, so these three reaction pathways of this oxygen reduction and some possible rate determining steps are there. So you can say A, diagram A, B and C are there, where A is the cathode surface pathway. You can see cathode surface pathway where you have cathode and this oxygen gas comes and gets absorbed at the cathode. Okay, then it gets become O absorbed, then it takes these two electrons to form oxygen ion. Okay. Other thing is, instead of surface, bulk pathway we can say, which is in which this oxygen gas is getting absorbed into the surface, into the in the middle of the cathode, into the pores of the cathode, where this electron goes there, and directly you are having your oxygen ion being formed. Okay, so which passes through the electrolyte to the anode side. So that is one thing possible, right? So one possible is only oxygen gets absorbed to the surface and it gets dissolved from the surface. Then that OO will react with the electrons to form oxygen ions. Second category is oxygen is getting into the pores of the cathode material where it combines with the electron on the surface itself. At the site, active site itself, which releases the O2 minus ions. Okay, so that is called bulk pathway, and there is another pathway called as electrolyte surface pathway, where this oxygen does not get absorbed at the cathode surface at all. What is happening is oxygen will form which absorbed at the electrolyte surface, then that will release the O2 minus ions by combining with the two electrons. Okay, so that is what happens when you say electrolyte surface pathway. So these three is possible to happen, and all three also can take place in different proportions. Okay, so this is again another diagram which shows you that what are the products that are leaving. Again, even you are using ethanol as a fuel, what will be the reaction taking place? Let us say solid. It's a typical solid oxide fuel cell. As I told, any hydrocarbon can be used, ethanol can be used, alcohol can be used, right? If you are blended ethanol or pure ethanol, you are want to send into the system. So what will happen if it is with water? Ethanol is reaching here. Okay, so we will be having some external reformer system, which where we are actually we do it externally, because if it is ethanol, what we do is we get a lot of heat through the reaction taking place in SOFC, right? That heat will be taken to this separate reformer where the main reaction is taking place, where hydrogen is being formed separate, and whatever hydrogen is formed from that system will be passed to the anode side of the solid oxide fuel cell. Then you are having air also entering from the other side. So these hydrogen and oxygen combine to form water molecule, which is the overall reaction when you use hydrogen as the fuel. Okay, so that is also possible. Externally, making use of the heat in a reformer to produce hydrogen separately from the ethanol, also a particular system which can operate. Okay, and this is the animation which shows you what is happening in a solid oxide fuel cell. Okay. Yeah.
A solid oxide fuel cell is an electrochemical device that produces electrical energy by oxidizing fuel. This system itself consists of a porous anode and cathode that are separated by an ion-conductive solid electrolyte. In this device, the fuel is oxidized at the anode, while the reduction of oxygen takes place at the cathode. These reactions are possible if the electrons participating in this process can move from the anode to cathode. But the only way to do that is to use an outer circuit. And that's where we can harness the electrical energy.
Okay, so with this background, we will get into how the solid oxide fuel cells was developed throughout the history. What is the research and development happened in the past 100 years? Okay. Remember, solid oxide fuel cell makes use of a solid ceramic electrolyte such as zirconium oxide stabilized with yttrium oxide instead of any liquid or membrane. Okay, so there is no polymer electrolyte membrane like Nafion, or there is no any liquid present here in the form of acid or alkaline. Okay, so what we are using is a solid ceramic electrolyte. So there is no liquid parts coming into picture like even in molten carbonate fuel cell. So what happened in late 19th century is conduction was not well understood that time. Later only Nernst observed that at the University of Göttingen that stabilized zirconia when it is doped with any metal like calcium, magnesium or yttrium, they acted like an insulator at the room temperature. They acted as an ionic conductor in the range of 600 to 1000 degrees Celsius, and they are a mixed conductor, both electronic as well as ionic, when it is above 1500 degrees Celsius. So here you get the answer for why solid oxide fuel cells are not operated above 1500 degrees Celsius or above 1000 degrees Celsius, because when these ceramics become electronic conductor when it is above 1000 degrees Celsius. What we want as what is the role of the electrolyte in a fuel cell? They should selectively allow the ions only to pass through it. They should not allow the electrons to pass through it. So at that high temperatures above 1000, they start behaving like a mixed conductor. That is the reason we don't operate around above this kind of temperature, beyond that temperature. Okay, so keep that in mind. And what is the main part of a solid oxide fuel cells? That is the electrolyte, which means that this main part was already discovered well before in that time itself. Okay, because that time itself he identified this particular material. It will act as an insulator at room temperature. It will act as an ionic conductor at 600 to 1000 degrees Celsius, which is the application for us now in solid oxide fuel cell, which is being operated around 600 to 1000 degrees Celsius. It is a very good material as a ionic conductor. Okay, so there we got the electrolyte material ready that time itself. Okay, but the fuel cell concept was demonstrated only in 1930s using this zirconium oxide. But there were many improvement required to make it a competitive device to other type of fuel cells. So that's why in 1950 itself, a simple straightforward design which was made, the cheaper manufacturing wasn't possible because of that simple design. This flat plate fuel cell, solid oxide fuel cell was made that time itself, 1950s. Okay. So if you look at this diagram, you have this history that has taken place. So reversing the electrolysis was made. We have discussed this in our introductory lectures of fuel cell. What is the history of this electrochemistry thing? Okay, so in 1905 to 1937, there were Wagner solid electrolytes were made up of gas, porcelain, quartz or mixed oxides of yttrium stabilized zirconia. Okay, and this Bard, Treadwell and Resis demonstrated solid ceramic fuel cells in this period. So even 1950 to 2000, solid oxide fuel cell development in USA and Japan has been taking place. They started making thinner electrolyte layer, lower ohmic losses with improved performance have been made. After that, in 2000 to 2010, the solid oxide fuel cell with planar and tubular design using stack was done, which has made this, because there are a lot of problems faced with the planar type of solid oxide fuel cells. Okay, so the lowering the operating temperature to 300 degrees Celsius using a thin film and nanocomposite electrolytes of 5 to 10 micrometer was possible when we moved on to the tubular design using the stacks. Okay, and 2010 onwards, a lot of interest towards perovskites have been coming into picture, so which influences the improvement of solid oxide fuel cells with the newer electrolyte materials kind of thing. Okay. So what happened? There were a lot of increased focus on perovskite electrode materials. So with that, the electrolyte-free fuel cell one-layer component device has also been prepared. Okay, which means that we are able to lower the operating temperature. We got some more economic one, and we even able to make some single component devices also. Because these perovskites have so many applications. Okay, perovskites you will learn about it in membranes, you will learn about it in solar cells, photoelectric voltaic cells, you will find it in solid oxide fuel cells, even in electrochemical sensors it is being used, it is used in battery applications, it is used in supercapacitor applications like that. Okay, so we have already discussed about these perovskites in molten carbon fuel cell also. There also it is used there. So even in solid oxide fuel cell also it is being used because of that good properties at operating temperatures. Okay, and this type of solid oxide fuel cells, what are the advantages associated? They are cheaper in cost, they are affordable power, that because cost reduction by lowering the operating temperature. We got fuel flexibility with solid oxide fuel cells and molten carbonate fuel cells also. We can use any hydrocarbons or hydrogen to as the fuel. Okay, ranging from all these things. And it is possible for power to all, even for small communities in a rural village, this type of power fuel cell can be used. Or even if you want to feed a large capacity population, there also high megawatt power plants can be kept. So that is a why modularity is there. We can start from millivolt to megawatt production, energy production is possible. And we have seen that similar to PEM fuel cell, this is also very portable and lightweight. Angle of fixing, designing, all that are simple. And you have green and clean power, and it is environmental friendly. So its efficiency with the overall efficiency, it's not a current efficiency, which is around 50 to 60. With when you recover the heat and use it in the system, in the power plant, say for example, we showing when methanol or ethanol is used, then you have to first to produce hydrogen from it, right? So there we are making use of the heat. In that case, the overall efficiency of the power plant becomes 80%, which is almost comparable with your combustion engines, all that. Okay. If you compare the technological growth and sustainable development, because this modularity is there, you can use a single cell, or so you can make any number, because it's the one cell, 5 cell, we have done around 1.5 centimeters. So that way you can make a large fuel stack with less space. Okay. And research is being carried out at the academic level as well as in industry also. They are trying with different ceramic materials, modifying it, composite materials have been developed. Okay. Let us look into some research advancements that has taken place. And these solid oxide fuel cells are most efficient devices which is invented, which can convert the chemical energy into electrical energy. Both electrodes, anode and cathode, are made of ceramic materials, because we are going to have high operating temperature, so which prevents the use of any other metals also. Okay. The big advantage of the solid oxide fuel cell or the molten carbonate fuel cell, we should know, because they are almost used in similar applications and their design are almost same. And this big advantage of the solid oxide fuel cell or that is the electrolyte here is solid and there are no pump requirement to circulate the hot electrolyte. In molten carbonate fuel cell, one of the limitations or challenges, we need a pump to keep circulating the electrolyte, because that ceramic, whatever material which is used, that should be always saturated with the molten metal, right? So we need a pump over there. And here the anode is made up of porous nickel for better electron conduction and catalysis. And we can have an operating temperature of 600 to 1000. And depending upon what generation fuel cell, there are different generations of fuel cell. This itself, first to second generation. When you say with increase in generation, the operating temperature is reduced. Okay. Because we are replacing some of the ceramic materials with other type. Okay. However, the thermal cycling can cause some cracking issue, brittle ceramic components, cracking of these brittle ceramic components. And you can make use of hydrogen and carbon monoxide mixture as the fuel. And even commonly hydrocarbon fuels can be used in solid oxide, like you can use diesel, natural gas, petrol, alcohol, all that as the fuel. That is advantage. We have very good flexibility of using any fuel as the fuel. Means anode side fuel. Okay. There are certain companies like Acumentrix, General Electric, Ion America, Rolls Royce, Siemens Power Corporation. They are interested in getting into this type of solid oxide fuel cells. Okay. And one of the company, you can see that Sulzer exists from Switzerland. They made a prototype of high temperature solid oxide fuel cells with 1 kilowatt of electric power generation system. Okay. And there are different strategies are being used in the solid oxide fuel cells. As I said, with respect to design, different design strategies for solid oxide fuel cells. One of the design strategies are using the hydrocarbon fuel in the solid oxide fuel cell. If you are using that case, what we will do is, in the first strategy, additional unit of reformer is added prior to the operation of the solid oxide fuel cell. As I told you, we shown you when ethanol is there also, then we shown the diagram. We are having a separate reforming unit, steam reforming unit, where hydrogen is being produced. That hydrogen and carbon monoxide will combinedly will reach the anode side of the solid oxide fuel cell. This hydrogen will form water and CO will form CO2. All that. Okay. So what is the role of the electrolyte? At cathode side, air is coming. From air, oxygen will react with the electrons to form the oxygen ions. Then that oxygen ion will be allowed to pass through the electrolyte selectively. So these oxygen ions and the water, hydrogen reacts to form the water reaction. We have seen already also. I will quickly move on to the next strategy. Another strategy is using the hydrocarbon fuel in the solid fuel cell. We will have an internal reforming, and we will have another extra coating of reforming catalyst. Okay, we can even say a mixture of anode plus reforming catalyst. So that way, this solid oxide fuel cell, where we want to have internal reforming, we will have a mixture of anode and a reforming catalyst. So there is an additional reformer layer, or you can even say while making the catalyst itself, reforming catalyst is mixed with the anode material and then made into a compost. Okay, so this is the second strategy, where we don't have a separate steam reforming plant in the system, in your plant unit in your plant, where but within the system itself, that means you are directly passing the methane into the system. Okay, so that way you are having an internal steam reforming taking place also. Then you have the different reaction taking place. Okay. So here the fuel will be mixed with oxygen carriers such as water, this carbon dioxide or oxygen itself into the solid oxide fuel cell, and the reforming process will occur on the anode itself, which is followed by the fuel oxidation by the anode layer. Okay. So hydrogen is produced on site. It is like on site production of hydrogen. Okay, so what is the general reactions of steam reforming, dry reforming, and partial oxidation is given here. You can see that hydrogen is produced from methane in the steam reforming step, and then partial oxidation, we have this methane reacts with oxygen to form carbon monoxide and hydrogen. So any reactions are possible. In all three reactions, you can see hydrogen being one of the product and carbon monoxide is the another product there. Okay, so this first and second strategies aims at adding the oxygen content to the fuel to shift the equilibrium of the fuel content away from the carbon forming region. Okay, so how the oxygen can be added? So oxygen can be added in the form of oxygen containing materials such as water, or you can add carbon dioxide, or you can add small amount of oxidation also. Okay. So these are the equations given out there, what reaction takes place. And we are having a third strategy of using hydrocarbon fuel in the solid oxide fuel cells. So the direct hydrocarbon utilization involves finding the catalyst that directly convert the hydrocarbon to water and carbon dioxide species. So the reaction is different here. There is no hydrogen production, then followed by water formation. Here, methane is converted to hydrocarbon is converted to water and carbon dioxide species. Actually, this strategy avoids the incorporation of any additional layer of material into the SOFC system, and thereby it reduces the step of reaction from hydrocarbon to carbon dioxide and water. So there are a lot of research is done to enhance the tolerance of solid oxide fuel cells towards the carbon deposition, because the stability of the solid oxide fuel cell over the time period and the output power density, all this will be affected if there is carbon deposition. Okay, so what we have to know is, whatever is the strategy of using hydrocarbon fuel cell in solid oxide fuel cells or other two, we have to examine the limitations of this methodology so that we can detect the carbon deposition. Okay, so even though there are several strategies and materials are available currently in the hydrocarbon fueled solid oxide fuel cells, let us focus on the use of cermet material as the anode for direct use of hydrocarbon in solid oxide with reforming or without reforming. Okay. So we need some improvement of carbon deposition, and long-term carbon deposition study needs to be done. So if you look at some of the mechanisms by which this carbon deposition is taking place, let us look in detail about the carbon deposition process. So these carbon species, which are usually they thought about that they will be present in amorphous carbon or crystalline graphitic form like that. But this, if you look at the carbon deposition process, we can describe that it takes place in 4 stages. What happens in 4 stages? Let us see. As you can see in this diagram, you can see with respect to time, you have stage 1, stage 2, stage 3 and stage 4. How the current density is decreasing with respect to time. And what is responsible for this decrease in current density, we should understand, right? So in the first stage, we have, that is the first stage is beginning of the time, right? So when time is during initial stages, that is during the beginning of an operation, there will be no carbon deposition taking place because it is fresh. The membranes, anode, cathode, pores are fresh, and there is no carbon deposition taking place. So what we will get is a maximum power density. So you observe a maximum current density also there. And what happens? So the reactant comes, because since the pore is not deposited with the carbon, so the pore is available for the reactant like methane to come and get deposited and absorbed, and then for the reaction to take place. Okay, so CO2 and water will be the product which can be formed. So even the passing of oxygen ions from the cathode side through the electrolyte and to the anode material will be taking place. So these methane and oxygen ions will combine to form carbon dioxide and water. So when there is no deposition of carbon, we have a reaction taking place at a faster rate. The kinetics is faster, which means that we have more current density, and we have output power power density is high. What happens with respect to time? There will be little deposition of carbon materials taking place. What happens? It is not covering the whole anode surface, but however it occupies certain places, which means that the methane and oxygen ion to combine, that reaction will get little affected. Okay. So what happens? This carbon was actually thought to improve the anode conductivity and may actually be observed by slight increase in the cell performance, such as if you look at this diagram again, in stage 2 there is little increase in the current density because there is little deposition of carbon material taking place in the pores of the anode material. So thereby we have little increase in the power density also. Okay. And what happens further is, with further time, what happens? The carbon begin to cover the whole surface. So what happens? The cluster of carbon will interconnect to form a layer. It is like a paint coating. The pores have been coated with carbon. So what happened? They act like a barrier layer. So this carbon, but however this carbon deposition is porous, so it will still allow the fuel gases to pass through it and react at the anode surface. So there is a little current density present. Okay. But what happens? But the reaction kinetics is slowed down here. So there is lower performance. That way we observe that in stage 3, the current density keep decreasing with respect to time, because the more the deposition of carbon layer becomes non-porous, there will be less diffusivity of the reactant through the pores to reach the surface, and so the reaction kinetics will be slowed down. So that's where we observe the lower current density. So this carbon deposition is porous and still allow the fuel gas to pass through and react at the anode surface, but at a lower rate, and hence lower performance is observed. Thus at this stage, the current voltage or power density will be observed to decline with respect to time progressing. Okay. And finally we have a stage 4, where the carbon which has deposited at the anode surface is completely blocked the passage of the fuels to reach the anode site and to combine with oxygen ions and to form carbon dioxide and water. So there is no reaction taking place, means what will happen? Current density will be 0. So stage 4, we have a condition where the cell will cease to operate. That is, there is no output current, there is no power generation taking place. So that way the cell power output is absence in this case. Okay. So what is happening? Some equilibrium studies of carbon, hydrogen and oxygen content in the fuel the relation to carbon formation is been explained. It is observed that the carbon formation will occur at the equilibrium depending upon the temperature, depending upon oxygen content. Okay, and fuel gas containing hydrocarbon only, like pure methane, are actually located in carbon deposition region at any given temperature. To avoid being in this type of carbon deposition region, the operating temperature should be raised to shrink the region as according to figure. Or what we can do, we can add oxygen source such as steam into the fuel mixture, which will bring the fuel mixture out of the carbon deposition region. Nonetheless, the equilibrium study only relates the tendency of forming this carbon deposition in the fuel mixture without the involvement of catalyst, such as in case of anode solid oxide fuel cell. So in this figure you can see some of the possible formation of different type of carbon deposition on a nickel anode material. So what happens initially is nickel will start depositing at the surface of this nickel. So but still it will be porous enough to allow the gases to pass through it, that is methane or any reactant to pass through it, and the surface reaction takes place. But later on what it happens, it forms a type 2 formation, because initially for any method the first type 1 deposition is taking place, after which this carbon start forming monolayer, double layer, like that, so which will retard the migration of reactants into the reaction sites. And later on what will happen, due to, you have seen different type of metal diffusion, so this carbon, based on the difference in the sizes of carbon and nickel, this carbon will start diffusing through the gaps and the vacancies and occupy the interstitial vacancy, and later it will result in the flaking and dusting of the metal. The same is represented in this diagram. So in general, this type of operation of a solid oxide fuel cell is very straightforward. Oxygen atoms are reduced at the porous cathode surface by the electrons. The oxide ions diffuse through the electrolyte to the fuel-rich and porous anode, where they react with the fuel and they gives off the electron to the external circuit, as I explained earlier. And there will be large amount of heat is being produced by this electrochemical reaction. So we have to have an integrated heat management system. So we have to recover the heat and make use of it. Okay. And initially what will happen, your operating temperature, room temperature is 30 degrees Celsius, or even summer here it is 40. So what will happen if you want to operate to 600 degrees or 1000 degrees Celsius? Initially it will take a lot of time to reach to its operating temperature. And we have seen that these electrolytes at room temperature are insulators, right? So what will happen that time? So it will take some time to get the steady state and get the power output, right? So this is best applications of this type of solid oxide fuel cells are, it will be use both the heat and electricity generator. So we will make it use of it as stationary power plant or auxiliary power plant. It's like in our apartments or hospitals, we will have a generator, right? Generators will take some time, at least 10 minutes to come in action, right? So the startup time problem can be solved if you are using a supercapacitor battery for the first few minutes of the operation in the remote applications or mobile applications. Okay. So what are the different components present in this solid oxide fuel cells? Now we know that apart from anode, cathode and electrolyte, important thing two are there. One is interconnector and another one is sealant. Okay, so those two, and what are the required characteristics of each material we should know. So in this lecture we have discussed even about the recent advancements in the materials that have been developed for molten carbonate fuel cells, and we have seen an animation video for molten carbonate fuel cell, and we have discussed about the principles of solid oxide fuel cells in detail and what are the reactions that is taking place, and we have seen the advantages and the challenges associated with solid oxide fuel cells. And we even discussed about the triple phase mechanisms, that possible rate determining steps at this triple phase boundary that can occur, and we have seen that whether we can have internal reformer unit or external reformer unit, or no need of We will make a composite for this material and reforming catalyst, all that. Different design strategies have been discussed in detail in this lecture. In the next lecture, we will discuss about the different components of solid oxide fuel cells, desired characteristics of the materials, and research advancements and recent trends with respect to new materials for solid oxide fuel cells, and what is an interconnector and sealant, what should be the material of choice for interconnector. All this we will discuss in detail in the next lecture. Well, in this lecture, we have seen in detail about the principles of solid oxide fuel cells. So there are various components present in solid oxide fuel cell in addition to molten carbonate fuel cell. Here we are going to have interconnector and sealants, because gas tight sealants are very important and interconnectors has to be connected to successfully collect all the electrons formed to be connected to the external circuit. So for each component like cathode, anode, electrolyte, interconnector and sealants, we should know what is the function first. If you know what is the function of the cathode, what is the reaction taking place, what is the raw material that is reaching the cathode, similarly what is the raw material reaching the anode, what is the reaction taking place, and with respect to electrolyte, what anion or cation, which ion is just to be passing through it, whether if it is oxygen ion. So accordingly we should know the required characteristics of each components, so which we will discuss in detail in the next lecture. So we will look into desired characteristics of cathode, anode and electrolyte. Also we will discuss about what are the various materials that have been used for anode, cathode and electrolyte, particularly for solid oxide fuel cell applications. We look into the history of those materials and recent advancements that have developed with respect to research and development or even commercialization of such solid oxide fuel cell. What are the components which have been used, what is the best combination for these solid oxide fuel cells, all that we will discuss in detail in the next lecture. Thank you so much for joining my classroom. Meet you in the next lecture. Bye bye.